Welcome aboard, where aviation concepts become simple. From instruments to aerodynamics, we make exam prep clear and cockpit learning faster. This is StudyKwik Aviation.
Welcome to StudyKwik. Today we'll explore altimeter settings and density altitude, a topic every pilot must master. Let's start with QNH. QNH is the setting that makes the altimeter read the elevation of the airfield when you're on the ground. Example, runway elevation is 270 feet. If QFE, the pressure at runway, is 995 hectopascals, then QNH equals 1005 hectopascals. QFE sets the altimeter to 0 on the runway, so during circuit flight leveling, height above airfield is directly shown. But QNH is more practical on cross-country flight levels. It lets all aircraft reference mean sea level altitudes. Now, what about QFF? In hot weather, pressure layers expand, so actual sea level pressure differs from calculated sea level pressure. For flight level planning, meteorologists use QFF, but pilots use QNH because altimeters are calibrated to it. Above it, all aircraft must use the standard setting 1013 hectopascals. This ensures separation even if local pressures differ. In the UK, transition altitude is 3,000 feet. It's a fixed level, regardless of daily QNH. Climbing through transition altitude, we set standard 1013. From then on, we fly by flight level instead of altitude. Example, flight level 60 means pressure level at 6,000 feet in ISA atmosphere. So two aircraft at flight level 60 will maintain safe separation anywhere. We just learned about transition altitude. Now, let's see transition level. Transition level is the lowest available flight level above the transition altitude. It changes depending on QNH. Between transition altitude and transition level lies the transition layer. Aircraft climbing pass through it, changing from altitude to flight levels. Example, transition altitude is 3,000 feet. If QNH is 1013, transition level may be flight level 40. But if QNH drops to 978, transition level could rise to flight level 50. So ATC will advise the correct transition level daily. This prevents aircraft crossing each other without vertical separation. Very important for safe IFR operations. Now let's move to pressure altitude. It's the altitude shown when altimeter is set to 1013 hectopascals. Why is this important? Because aircraft performance charts are based on pressure altitude, not indicated altitude. Formula, pressure altitude equals elevation plus 1013 minus QNH times 30. Example, airfield elevation 270 feet, QNH equals 1000 hectopascals, pressure altitude equals 270 plus 1013 times 30 equals 270 plus 390 equals 660 feet. If QNH is higher than 1013, pressure altitude will be lower than airfield elevation. If QNH is lower, pressure altitude will be higher. This shows why pressure setting is critical for accurate performance calculation. Now, let's look at density altitude. It tells us how the aircraft will perform under given conditions. Density altitude equals pressure altitude corrected for non-standard temperature. If temperature is higher than ISA, density altitude increases. That means aircraft behaves as if flight level at higher altitude. So takeoff run becomes longer, climb rate reduces, and engine power drops. Formula for correction, density altitude equals pressure altitude plus 120 times OAT minus ISA temp. Example, pressure altitude equals 5,000 feet. OAT equals ISA plus 15 degrees Celsius. At 5,000 feet, ISA temp equals plus 5 Celsius, so actual temp equals 20 Celsius. Correction equals 120 times 20 minus 5 equals 120 times 15 equals 1,800. Density altitude equals 5,000 plus 1,800 equals 6,800 feet. That means the aircraft performs as if it's at 6,800 feet, not 5,000 feet. Notice, higher density altitude reduces lift and engine power. This is why hot and high airports are challenging. Now let's compare. If OAT is ISA minus 10, density altitude will be lower than pressure altitude. Lower density altitude improves climb and takeoff. Higher density altitude reduces performance. Pilots must always calculate density altitude before flight level. It directly affects safety. Let's summarize the altimeter settings again. QFE equals height above airfield. QNH equals altitude above mean sea level. 1013 equals flight level. Transition altitude equals set standard 1013 climbing up. Transition level equals lowest available flight level descending down. Pressure altitude equals elevation corrected to 1013. Density altitude equals pressure altitude corrected for temperature. Together, these allow pilots to flight level safely, avoid collisions, and plan aircraft performance. This is the foundation for understanding advanced topics like climb gradients, performance charts, and high-altitude flight level. Now you've got a complete view of altimeters, settings, and altitude types. Thanks for learning with StudyKwik. If you found this helpful, please like, share, comment, and subscribe.